Start with the solution of the problem that we just read, class. So I'd like to discuss first uh, the formula for determining the slope of the line, connecting the points, representing the concentrations of our phases, the bulk phase 1 and the bulk phase 2. So bulk phase 1 is the mixture of the liquid and the gas phases at the bottom of the column, and bulk phase 2 comprises of the liquid and the gas phases at the top of the column. Now, when we connect these 2 points, of course, they have y1 and x1 as their concentrations for bulk phase 1 and y2, x2 for bulk phase 2. If we're going to connect these 2 points, we'll have the operating line. And the line that I have drawn here passing through the origin is the equilibrium line. Now, if we drop a line of slope equal to negative k sub x prime a divided by the quantity 1 minus x sub a subscript in all over k sub y prime a divided by the quantity 1 minus y sub a those quantity subscript in to this line, which is your equilibrium line, you will have the point M1. Now P1 now is being, shall I say, projected through the equilibrium line, and that particular point is M1, representing now the concentration of the interface that is made when the two phases B1, L1 forms the bulk phase 1. Okay, so this particular point, let's say we'll label it as M sub 1, the interface. So these two connected points now found in the operating line, P1 that is on the operating line and M1 on the equilibrium line has this slope which I just read a while ago. Now we do the same projection on bulk phase 2 point, P sub 2. We project it on the equilibrium line, and that particular point where we drop it on is M2, labeled as M2. Now these two lines are parallel, P1 M1 and P2 M2, and has this same slope. So it's the same slope here, which I have just read a while ago. Now the concentration of the interface will now have, aside from 1, in its subscript, the letter I, small letter I, meaning it's the concentration of the interface. So Y sub I1 for the concentration of the gas phase in the interface, and X sub I1 for that of the liquid phase in your interface. To do the same rather representation of concentration for interface M2 is copied. So you have Y sub I2 and X sub I2. Now if you drop your P sub 1 point right on the equilibrium line and read its corresponding gas phase concentration, that would be Y sub 1 asterisk for bulk phase 1. So it's the equilibrium concentration of the gas phase for your bulk phase 1. Now we can have the same procedure done for bulk phase 2. If we drop it directly, we drop the point, project it directly vertically down on the equilibrium line, we will have Y sub 2 asterisk for its equilibrium gas phase concentration. As for its x2, it's just the same as the original, because anyway, this point P2 has x2 and y2 as its original concentration. So we just determine the gas phase equilibrium concentration equivalent for the two phases, P sub 2 and P sub 1, and it's represented here as Y sub 2 asterisk and Y sub 1 asterisk respectively. Now the slope of the line connecting P1 and M1, P2 and M2, as written here, will also be equated to these two equations. Okay, y1 minus yi1 over x1 minus xi1. So in here you have in this formula you are using the concentrations of the phases at the bottom of the column, where in here we have the concentrations at top of the column. If our solution is dilute, we can simplify this particular equation. Why I say simplify? Because the formula for this one class is complicated. I will show to you in a little while. So if the solution is dilute, just like in the case of our sample problem, it's dilute, we can opt to using this simplified version. So instead of dividing by 1 minus x sub a whose quantity subscript im, same thing here in the denominator by this one, we can simply divide by 1 minus x1 for the numerator and 1 minus y1 for the denominator. Okay? Now, let's go to our problem. So if our problem, the problem that I just read, is represented in terms of a very simple illustration. So this is your column. You have here the concentrations of the gas phase entering and leaving the column, and you have here your liquid phase. The cross-sectional area, which is 0.213 square meter, is also represented by S. If we use the method of the film coefficient or mass transfer coefficient, so A, cross-sectional area, is also S. Now, I have indicated here that your gas phase flow rate is based on the inner part of the gas, which is just the air, and its prime, 11.43 kilogram mole per hour. For our liquid solvent, since it's all water, then it could be represented as L sub 2 prime or simply L prime, okay? Because our solvent is pure water. I have placed here the mass transfer coefficients and the very important condition of equilibrium, okay, as stated in the problem. So our first procedure will be using the film coefficient, and we'll be using the gas phase film coefficient or mass transfer coefficient because the problem is gas absorption. And this is the formula for the equation rather, where you can find it in Genco place. You have k sub y prime a, so this is your mass transfer coefficient. Z is the column height. You have y minus y sub I whose quantity subscript m. So this one we need to determine, and it's equated to B. This B is the average of B1 and B2. S is the cross-sectional area, and Y1 and Y2 are the gas phase concentrations at the bottom and at the top of the tower respectively. So if we are to determine the average flow rate of the gas phase entering and leaving our column, then we need to use the formula B prime, B1 prime or B prime, B2 prime or B prime, because they are inner, the same inner parts are present in both of these phases. Then B1 should be multiplied to 1 minus Y1. B2 should be multiplied to 1 minus Y2 to give B sub 1 prime and B sub 2 prime respectively. So solving your equation based on B sub 1 and B sub 2, so you'll be able to get B sub 1 and B sub 2 here, get the average, we have it down. Now, in terms of our formula, then we have this already. Just change my partner so you can see it. So we have this already. This one is given in the problem. These small fractions are given in the problem. This one is given in the problem. So meaning, if I need the Z, I need to find this one. And the formula for that is written below. So let me just clear my marking so I can spell that. So the formula for the quantity y minus y sub im is this. Okay? Now in the formula, you could see that we have y sub I1 and y sub I2. And we don't know this because these are the concentrations of the liquid phases in the interface. Okay? So, but we have this formula shown to you in the figure a while ago, relating the slope for the dilute solution. So, you see this one, we use the 1 minus x1 and 1 minus y1 because our solution is dilute. So, instead of, let me go back, of using this original equation for the slope, we use this one because our solution is dilute. Okay, so now we have this and we equated it for now with the first of the two equations wherein it's equivalent to. It could be equated to this one or this one. In this case, it was equated to the first. Okay? Now in here, you could see that you have two unknowns, y sub I1 and x sub I1. So meaning, using this equation alone, you won't be able to find yi1, which you need here, because you need xi1 or x sub I1. The equation that you could use relating y sub I1 to x sub I1 is the equilibrium equation. Y sub I1 equal to mx sub I1, or simply your y equal to mx equation. We just change specifically the y and the x as to what y and x need as a pair. Okay, in this case, we need the concentrations at the interface at the bottom of the point. Okay, so we have yi1 and mi1. However, class, you could see here, even if this is the simplified formula for the dilute solutions for the slope, we need the x1. We don't have that. We only have y1 and y2. So one way of getting x1 is using the component balance wherein we're utilizing the inert stream. So you have L primes and B primes here. And together with these L primes and B primes, we use the mole ratios, not the mole fractions. Now with x2 0, because our solvent is pure water, and y1 and y2 known, we can determine x1. And our x1 is 0.00467. Okay, now we have it, so meaning this side is okay already because we have everything there. So we just need another equation to relate yi1 and xi1, which is this equation 2. If it's this equation 2, then there's a need for you to determine the m. How are we going to determine the m? Okay, so we'll proceed with what we have here below. We substitute. So you have this and you have that. So these are now the two equations for the slope. One in terms of yi1, xi1, and yi2, xi2. Just substitute the values of the concentrations that are known already. If you're wondering what are those equations, okay, which we equated to this, because our solution is dilute. Now, if we go down, so we have an equation here which has two unknowns and that cannot be solved. And we need another equation, the y equal to mx. So we use this fact that partial pressure of acetone is 30 millimeters mercury when its mole fraction in the liquid phase is 0.088. So we first use the partial pressure to determine its mole fraction in the gas phase. Excuse me. So we have 0.03947 and equated to m times 0.033. So now we know that our slope is 1.185. This 1.185 could be used to any of these for any of these two equations. Equations relating xi1 to yi1 and xi2 to y. Now, since in here we need in equation 3 xi1 and yi1, so we will use this. Solving the two equations simultaneously will help us solve this one. And for this, we will have the same equation. And we can solve for xi2 and yi2 also. Okay. Now, this one, where did we get this equation? It's taken from this one. So instead of equating the slope here to this, now this same slope value, which is negative 1.73051, this time is equated to this one. The resulting equation is solved simultaneously together with this one. Okay, y2 equal to 1.185 xi. In the process, we get now all four concentrations at the interface. xi1, yi1, xi2, yi2. So since we have everything complete, we need to go back to our y minus y sub I close quantity subscript m and solve. So we have this now. Since this is the last information we need, if we substitute it in here, in our original equation, the original equation is this one. We will solve for the z. Be able to solve for the tower height, which is 1.363. Now, if you're wondering what is this 3,600 seconds per hour, we converted our time here because time unit, because in the right side of our equation, our time unit is in hours. Right in here on the left side, it's in seconds. So it's either way, which way you do it, either you convert on the left side or you convert on the right side. But what is certain is you need to convert. That way your units will be dimensionally homogeneous. Okay? For procedure 2, this is just for illustration purposes, class. What if you use the film coefficient or mass transfer coefficient of the liquid phase, K sub x prime A, which is actually for the process of stripping. So you have a different formula here to use. So this is the formula that you'll be using. You have this different expression, quantity x sub I minus x close quantity sub m. And instead of the v, now you're using the L, and instead of the y, so you're using the x. So in the same way here, your L should be the average of the two L's, the L1 and the L2. So we determine L1 and L2 and get the average and place it in here. So the next thing that we need to determine is x sub I minus x close quantity subscript m. What is the formula for this? So you can see it here below. So this is your formula for x sub I minus x close quantity subscript m. And since we know already from procedure 1 all interface concentrations and all mole fractions for all the four phases, L1, L2, P1, P2, then we just substitute in here. So meaning if you started with this procedure, the length of the process that you used in procedure 1 will be the same for this, because you also need to determine again the concentrations of the interface. Now, knowing this one, go back to the original equation. This is the original equation and substitute. You'll be getting, a value of 1.349. So instead of 1.361 or 36 something, it's now 1.349. So the variation is not that much, but there is really noticeable variation because we use the liquid phase mass transfer coefficient or film coefficient, not the gas phase. Okay? For procedure 3, this is using the number of transfer units where Z is equal to HG and G. And this is applicable for dilute solutions also. You have here the formula for Ng. This is your formula. Hg is this one. Okay, we know already the V from procedure 1, so it would be the average. We have this and we have the S, so you can solve for the Hg right away. And this is the value of the Hg. As for the Ng class, it's just this one and the Y minus Y sub I subscript cross quantity subscript M in procedure 1. So we determined that already, so we'll just copy. If we do not have this yet and we're starting the procedure 3, or this is procedure 3 that we're solving. So there's a need for you to do this. There's a need for you to do this. Everything that was done in procedure 1 to determine, where is it? To determine the quantity y minus y sub I subscript n. And this is your answer. So 1.363. So comparable to that of procedure 1 because we're using HG and G. Should we have used HL and L, there will be corresponding deviation from the 1.361 correct answer. Okay? Now, so this procedure has the same answer more or less as procedure 1. So procedure 4, this time uses the HETP. But the one wherein if you are going to base it, if you're going to determine HETP based on the hog value, then you are assuming that the slope of the equilibrium line and the operating lines are straight. In this case, you know that the slope of the equilibrium line is 1.185. So we need to determine the slope of the operating line, which is easy. You already have the y1, x1, y2, x2, so you just determine the slope. So if the two slopes are comparable, let's say one is 1.185, another one is 1.182, 81, or 79 even, that is more or less okay. Because we can consider that our lines are more or less parallel. But in terms of accuracy, of course, it's not your answer here using this procedure will not be accurate because a slope of 1.185 is really different from 1.183 or 180 in that matter. But these are the formulas, and you can see in the formula that this is no coincidence, class. I'd like to make it up. This is no coincidence that you see here a capital K sub y prime A. So if it's a capital K sub y prime A, it's the overall gas mass transfer coefficient. It's not just the gas transfer coefficient, so overall. So we need to have a formula then to determine this one because what we know are just this and this. Okay, so this is the formula that he will use. That way you will be able to determine the capital K sub y prime A, which you need here in the hog, which you need to substitute here to find the HETP. Now, in the formula that you are seeing in class, this one is not known, this one is not known. So meaning you need to determine it and this one. Okay? How do we determine those? So you have here the formula for the quantity 1 minus y subscript im. And since we know already all concentrations, we just substitute. For the quantity 1 minus x, the closed quantity im, so this would be the value. Now, you could see this one, the 1 minus y asterisk subscript m. So let's say we'll have an equation relating the y sub 1 asterisk to x sub 1. So in this case, your slope is the 1.185 and your x sub 1 is the x sub 1 that we determined from procedure 1. So your y sub 1 asterisk is 0.00552. Okay, so we don't have any problem with these two now. It's okay, but we have this one to determine path. So let's check. Your 1 minus y, your quantity 1 minus y asterisk subscript m is this. So that's the reason why you have y sub 1 asterisk because you need it in here in the formula. Okay, so in determining the y sub 1 asterisk and the y sub 2 asterisk, so you need the slope and you need the x sub 1 and the x sub 2. Now you can substitute values here and now you have the capital K sub y prime A value. As for the hog, just substitute. This one is still the average of the two B's. We now have the capital K sub y prime A and just we have also the cross-sectional area as given in the problem. That's the S. So if you substitute everything here on equation 3 for procedure 4, you will have this as the answer, 0.54124. For the HETP, you use this value and the gas absorption value here. You know how to find the gas absorption value anyhow. So the gas absorption value, where is that? Here in the HETP. So your HETP is 1.000023. As to finding the gas absorption factor, since the two are really far from each other, so meaning your operating line is not entirely straight, since the gas absorption factors are not more or less comparable, so we need to determine the geometric mean of the two gas absorption factors. So this is the geometric mean, and this is your Krimser equation using theoretical number of stages. Using procedure 4. Okay, the hog is B over K sub Y prime A, capital K, that is times S, and once you have that, you need your gas absorption factor here to be substituted in equation 2 to get the HETP. In that sense, it's done here. You have the hog, and you have here the gas absorption factors. This one here, it's already substituted in here to get the HETP. The HETP, when multiplied to the end, will give you the C. Procedure 5 is also the procedure which uses the gas phase mass transfer gas phase number of transfer units. You could see here Hg and G, and we know already Hg here is our Hg. This is our Hg, so we just substituted. So if you don't have the Hg, then you have to do the procedure in the previous procedure that we can so that we can have the value of the A sub G here. Now this procedure 5 I've used just for illustration purposes again. What if the formula that we use for Ng is for non-dilute solutions? Remember, this problem of ours is dilute. The feed gas is dilute. So this is already your Hg. Your Ng for dilute solution is this one, and this particular integral, which can only be solved using numerical integration, has this as the equivalent. So good, because we know this already from procedure 1. And y1 and y2 is given in the problem. So then, if we substitute our answer here, so this is 4.21053, and this is your 1/2 ln. You have y2 and y1, and this Ng will be multiplied by Hg, which is 0.32376. The answer is 1.3668. So meaning, why did I use this one? Even if we use a formula for non-dilute solutions, for the number of transfer units based on the gas phase resistance, your answer will not vary much from the answers in procedures 1 and 3. So this is 1.366. So ang procedure lang gid nga hindi siya mayo lapit. Ang value is procedure number 4, because this one uses or is limited on the scenario that your operating line and your equilibrium line are parallel. And your procedure 2, which uses the liquid phase mass transfer coefficient. Okay? This is how you determine the column height for our tower using 5 different procedures. So in these 5 procedures, you already have the number of transfer unit procedure, the mass transfer coefficient procedure, and the HETP procedure. Okay, should you have any questions, feel free, class, to message me, especially regarding this particular solution. Okay, bye for